Hi guys. Back in February we covered 10.1 to 10.3, and just so I can remind you, 10.1 we were just talking about the rotational variables. 10.2 we talked about the kinetics or kinematics of a situation where alpha is constant in a rotation. So we did that. We did a lot of problems on these things. And 10.3, how to go between linear and rotational quantities. So these equations here. And also we were talking about centripetal acceleration, of course, and so forth. All those things we've done. But we didn't take it any further. We just did kinematics. Okay, we didn't look at energy or any of the other things that have rotational, linear and rotational correspondence. So linear would be like our x, v, a, and then rotational is our theta, omega, and alpha. And how they correspond back and forth, right? We didn't go into, that's a V, by the way. We didn't go into forces or momentums or mass, for that matter. And what are the rotational versions of those things? And so or energy, which is what we're going to start with. So we didn't do any of those things. So now get ready, hold on to your hats, because here we go. All right, so we're going to do those things now. So let's do it. We're going to dive into our fixed axis of rotation motions, all the things that happen as a result. So the first thing we're going to talk about is rotational kinetic energy, and that's going to lead us to the moment of inertia. So we all know that linearly, kinetic energy is 1/2 mv squared, right? Everybody say it together, 1/2 mv squared. Okay, v happens to be r omega squared. So we can say r omega squared, v equals r omega. It's not acceleration, it's v. R omega. V squared then is going to be v r squared omega squared, and we're going to take that v squared and we're going to substitute it in for that. Cake, everybody sees this. So I like to write it like this to distinguish between rotational and linear. I mean, it's pretty obvious that you're going to write it out. When you write it out like that, it's pretty obvious that that's what you're dealing with. However, what is it? What is it that we are actually looking at? What is the thing that we're looking at the energy of? So here's our circle. We've got a center of the circle. I don't know why it's happening. Who knows why? Maybe it's the moon going around the earth. Maybe who knows? But for some reason, there's some object that is circling the other, the center. Okay, and it's circling at a radius r. So who knows? Let's give it a direction. Let's have it go in that direction. So yeah, we don't know. Why is this mass moving in that direction? Nobody knows. So that's omega. All right. So in this situation, in this situation, this rotational system has a quote-unquote mass, okay? So this object, of course, has a mass, and if it were to go straight, it would maintain its linear velocity such that it has a linear momentum, okay? And we can draw that. We could draw it if I didn't put this in the way. We could draw that Vt, all right? And we'll put our omega on the inside here. Okay? So, sweet. That's what happens. This mass wants to go there, and if we want to find the kinetic energy of that object, all we have to do is figure out what its velocity at any given amount of time. And of course, we're going in a circle, so that means the velocity really doesn't change. The magnitude of the velocity doesn't change. Its direction does. So, in fact, why don't we just get rid of those and deal with it absolute value. Okay, so fine. This thing's going along, and we can calculate what its 1/2 mv squared is. All right. So rotationally, however, we're going to write the same equation like this. And if we notice, this bit right here, that's our velocity, rotational velocity. And then that leaves this here. What is that? What is that thing? Well, in our system, the way we've decided, we've got this mass going around in a circle. The only thing that there's nothing really other than a force of gravity or some force somehow is holding it in a circle, okay? So there's some centripetal force holding it into this circle, and it's going around and around and around. But what is this? Instead of that being our mass, okay, it's the rotational equivalent of mass. And we call that a moment of inertia. Why don't I just write moment of inertia instead of inertia? Moment of inertia. So that is, in this situation, in that situation, equal to mr squared. Now, other situations have different moments of inertia, okay? So you go through and you figure out what your moment of inertia is depending on the situation. Believe me, we will do it in a little bit. So, great. That's all fine and dandy. So what do we have? We have two things. Here, I'm going to go back to this. We've got mass, and now we've got moment of inertia. We use the symbol I for moment of inertia. Okay, so capital I. So that's the equivalent of the moment of inertia. Energy is just energy, so we're still going to measure energy in joules. We'll get to momentums and forces later, but for now we have done our thing. So moments of inertia, big deal, okay? And it really is. There's a lot to it, and we're gonna investigate it. So now, what happens if I've got another mass? What happens if I put another mass right here? It's also doing the same thing as the first mass, but it's just going around. In fact, we can call this one M1 and this M2, and I don't know, maybe we've got M3 and M4. Who knows? There could be a whole chain of M's. Okay, Mn. All right. So now, what we could say then, and each of them, I don't know, maybe each of them has a different, like planets in a solar system. Each of them has a different radius. So that could be R1, and this is M1. And over here we've got M2, and that's R2. Okay, are you with me? We could have all kinds of them, and we could have 8 or 9 planets or 100 satellites, or we could be looking at all the dust that goes around one of the rings of Saturn. But we have a question. We say, oh man, I really want to know how much kinetic energy all of that has. So I know that it's going to be 1/2 something. And if I add all of those things up together, from I equals 1 to n, let's say we've got n of them, then I can say mi times ri squared, all of that times omega squared. Okay? This is my moment of inertia. You guys can see why I didn't want to write the M earlier, because it's just I, right? Our moment of inertia. That's our moment of inertia. So what does that mean? We can then say our kinetic energy is really equal to 1/2 I omega squared. And this is the same analog equation to our kinetic energy linear, which is 1/2 mv squared. Okay, so we've got rotational kinetic energy, and we've got our linear rotational energy. Our linear kinetic energy. All right. So figure 10.2, 10.20. Figure 10.20. It has eyes for many shapes. And different axes of rotation. So you can go to figure 10.20. Hold on, let me see if I've got it here. There it is, 10.20. And so, yes, we're probably going to talk about how to calculate one of those. But for the most part, you just have that, and then you go to that and you say, oh, okay, now this is what I want to use for my moment of inertia. So you don't actually have to calculate it every time you want to do something. You can go to that figure and get your moment of inertia. So let's talk about many shapes, different axes of rotations, all of those things, but let's work with the, which one do I want to do? Solid cylinder of length L, radius R. Let's do that. Solid cylinder, length L, radius R. So let's draw that out. So here, gotta draw it out. There's a center of mass in there. The whole thing has length L. It's uniform, so L over 2. L over 2 from the halfway point to the end. Let's see. This is the radius R right in there. And we can have all different kinds of axes, okay? So where might be our first axis? We could do on the one end of it, we could have the whole rod go rotate like this around axis 1. I don't like any of what I'm doing right now. That's terrible. Axis 1. Okay. Then we've got another axis right down the middle, right where the center of mass is. That's axis 2. Then we have a third axis going right down the middle in that direction. That's axis 3. All right, so we're going to talk about the different axes and their different moments of inertia. So those are the 3 axes. We can look at we can look at that thing and notice that if we want to do axis 3, it would be the second down on the left. So second one down on the left would be our axis 3, and we could say then our moment of inertia, I'm going to put a little 3 on there for axis 3. Our moment of inertia is the mass of the object. We got to give it a mass. So it would be the mass of the object times the radius squared of the object, and then we're going to divide that by 2. Okay, so that's the moment of inertia if we were to go about axis 3. What if we were to go about axis 2? No, let's do axis 1 first. Let's do 1. Okay, about 1. So what are we dealing with? We're dealing with the picture on the right, 3 down. Okay, 3 down on the right. And we can go over and say that I is equal to our mass of the object times the length of the object squared, and we're going to divide that by 3. Okay? So that's going about axis 1. We've already nailed down axis 3. So we have yet to do axis 2. Let's do it. And axis 2, which one is that? Well, we're not dealing with a thin rod. We're dealing with a disc. So we're going to go to the right column and go down 1. And that's our solid cylinder or disc about a central diameter. And we're going to write down what our... So we've got the mass of the object times the radius squared. And we're going to divide that by 4. And we have to add the mass of the object times the length squared and divide that by 12. Okay, so why is axis 2 so much more complicated than the other two? Well, here's one reason. If we were to look at just axis 2, let me see if I can draw a good diagram of this. So there's this is our rod. Okay, it's not super long, all right, and it's fairly fat. There. And then we've got an axis of rotation going right down the middle of it. So it's going to spin around the middle. So we have to have something that deals with all the mass that's in this direction, but also it's got a width. All the mass that's in that direction we need to deal with as well. So it's not just axis 1 and all of it extending out this direction. It's not axis 3 where everything extends away from the center axis. It's got 2 dimensions of stuff that we need to deal with. One is in the R direction. That would be this one. And then one's in the L direction. And that would be this one. So we need to do something for both, okay? And considering both ends up giving us this. Okay, that's the proper way. And I mean, unless you're taking Calc 3, you probably haven't dealt with this, or if you are taking Calc 3 currently, you may end up figuring out moments of inertia for some object. It's fun. It's a good time. Everyone likes doing it. I think everyone likes prune juice too, so, who knows. All right. Now, if we were going to make it a very thin rod, okay, so now the radius is such that it's quite a bit smaller than the length, okay? In this situation, then I2 equals our ML squared over 12, okay? Because this one's going to dominate this equation, okay? This I2 equation, this guy gets so small, this one gets small, and this one's big. It's such a big difference that you just may as well do this, okay? So that's with a very thin rod. And if you look on the diagram there, in the figure, it would be on the left column 3 down. And you can also do the right column 3 down and get your thin rod about axis through one end, okay? Which is essentially what we did to get this I1, okay? So there you have it. Now, what are we going to do next? We need to calculate. Get out of here. I want to calculate a moment of inertia. All right, that's our job. How are we going to do it? So let's do a thin rod. So that keep it nice and easy. And we're going to do a thin rod of length L. So, and I'm going to look at it from a complete side angle, and we can define our coordinates like this. We'll make that the Z direction. And I think I'm doing this just like they did in the book. So you guys should be able to follow me and then go through the book and then come back and go back and forth and you'll get it, okay? So what are we going to do? We're going to rotate about this Z axis, all right? So that's our axis. The whole length is L, so that means from the axis to here is L over 2, and from the axis to the other end is minus L over 2. And again, because it's a thin rod, L is a lot greater than R. Okay, so we don't have to think about R. We're fine there. Now, let's do a little small dm. Okay, we've got a little small dm. This rod also has a unit mass per length. Okay, so the whole mass divided by the length is our mass per length. That means that the mass of the whole thing is equal to lambda times L. And then if we want to find dm, then that's just lambda dl. All right? Because of this, it's like a density. It's our linear density. Okay, so it's always important to either, if you're doing volumetric stuff, you want the density or volumetric density. If you're doing linear stuff, you want the linear density. We're doing linear. We're going to go from we're going to actually integrate from here to there in the end. Okay, so so far so good. Now I is equal to that sum that we talked about earlier, right? So there's this sum where we're doing mi times r squared, and we're summing it up from I equals 1 to n, that kind of thing, remember? Well, we're going to do that same thing, but instead of a sum, we've broken it down into the dm of the whole situation. So what does that mean? That means at every step of the way, our r is going to change. So I is going to equal, and we're going to do r squared dm. Okay, but in our situation, we're going to turn that into I equals negative L over 2 to L over 2. And we've got x squared. Okay, why x squared? Because that's our radius. So the distance from our center to here is x. All right, we're going to call this the... Actually, we're going from this side that way. So really, technically, our x is growing like that. Let's get rid of that bit. So x is going from L over 2 all the way to the end, minus L over 2 to L over 2. There's a reason you choose your... there's a reason for choosing your limits the way that you do. Like, why didn't we start out at 0 and go all the way to L? Right? There's all kinds of reasons. So, fine. dm equals lambda dl. And then, of course, dl equals dx. All right? Because they're equivalent. So I have to write down now minus L over 2 to L over 2. We're going to have x squared. We've got lambda in there. And then we've got our dx. Okay? So, fine. Everything's so good. We can rewrite this as lambda out front because that's a constant. It's not going to change. We're going to go from minus L over 2 to L over 2 and x squared dx. You guys know how to do this. You're so good at it. That's going to leave us with lambda x to the third over 3 from minus L over 2 to L over 2. What do you know? Let's take that 3 out front. And then we can do L cubed over 8, right? Minus L cubed over 8. We need a little more room here. Is that too much room? Yeah, we don't need that much room because we want to keep our picture. That's better. Okay, so far so good. Minus a minus is a plus. So nice work by us. We've got 2 of them. 2 divided by 8 is 1/4. So I'm just going to leave L cubed over 4 here. And that leaves us with lambda L cubed over 12. But now we can also go back up and notice that M equals lambda L. So I take one of the lambdas, leaves me with 2 lambdas, or I take one of the L's and multiply it by lambda. That gives me my M. Then I've got 2 L's left over, so that's nice. And then I have my 12. So we end up, see how the negative sign helped when we did our integral? Yeah. So anyway, you can do it any way you want, but it makes it nice. Anyway, that equals our moment of inertia, and that's the moment of inertia for a small, thin rod, okay? Or a thin rod, I should say, of length L. Okay, so this is how you do it. And technically, you really didn't need Calc 3, right? You didn't need it. You could do all of this with Calc 1, no problem. So, good job. Now, the next thing I want to do is called the parallel axis theorem. And this is definitely on the test. This is testable stuff. In fact, I think I remember having it on my test when I took your class. And I didn't have any idea what they were talking about. So I am going to, the parallel axis theorem, I'm going to lay it out for you, and hopefully I'll do it in a way where it kind of makes sense, and then you guys can understand what we're talking about. Okay, let's go back to our thin rod. All right, I don't know why that line got so thick at the end there, but there's our thin rod, okay, length L. We're going to have an axis down the middle of it. So we've got L over 2 on each side. And of course, that's where the center of mass is, right in there. And if we were to do it, we just found our moment of inertia about this axis. So if we were to rotate about an axis through the center of mass, we could say that our moment of inertia is equal to ml squared over 12. Okay, so let's just keep that in our back pocket. All right, in fact, we could call it ICM if we want. Okay, that's our I for the center of mass. However, what if we want to know this moment of inertia about this axis? All right, so let's call this axis 2. And we want to know what the moment of inertia is about axis 2. So, okay, that's great. The parallel axis theorem allows us to do this, okay? So we can, as long as we know the center of mass axis of moment of inertia for the center of mass, we can do this. So here's how it works. You say, I want my moment of inertia about some other axis. Okay, parallel. It's got to be parallel. This axis and this axis have to be parallel. Okay, otherwise it doesn't work. It's called the parallel axis theorem for a reason. Okay, they've got to be parallel. So we make them parallel, and then we say, well, that equals the center of mass moment of inertia, which we know, we just figured it out, plus the mass of the object, so whatever the whole mass of the object is, which is known, times the distance squared, and that d squared is the distance between the two axes. So d equals distance between axes. Okay? So that distance for us is this L over 2. Okay, so L over 2 is equal to our d in our situation. So we can write down then that our parallel axis moment of inertia is ml squared over 12 plus our mass times L over 2 squared. All right, so let's do that. Do a little math here. We can factor out m, and then we've got L squared over 12 plus L squared over 4. If we multiply, I'm going to call this PA, okay, parallel axis. Multiply the one on the right by 3. Then we end up with 12 in the denominator, and we've got 4 of them on top and 12 on the bottom. So that means we've got 3 on the bottom. So we end up with ml squared over 3. And if you go in your book, like I just did, you'll notice that that is exactly in the right column, third one down, that's exactly what you get for this situation. So our parallel axis theorem works because it gives us I for a disk when it's rotated about the end. I for a thin rod. I should say thin rod, not a disk. Okay. And just to make sure that we all know that that's what's happening, I'm going to write it down as ml squared over 3 about axis 2. All right, so we used the parallel axis theorem, and we got it to work. So keep in mind that there will be a test question on the parallel axis theorem, and you're going to have to use it. And it's not going to be easy to do it any other way. So once you're given this, it's easy to come up with this, right? So you want to use the parallel axis theorem when you get the chance, all right? Anytime you get the chance. It makes your life easier. And that's what it's all about, making everybody's life easier. Okay. Let's do a compound object. All right. Like a mallet. Let's do a mallet. Some people call it a hammer, mallet, whatever. Majolner. You can do this object, okay? That's the center of mass of that object. And then you can have this object, and it's all going to rotate about some point, and we're going to rotate, I don't know, like this, so that the mallet goes around in a circle like that. All right. And we could say that there's some distance d between the center of mass and the bottom of the head of the mallet. And then there's also some L, which is the length of the rod holding the mallet. Okay, so we've got a heavy part, like, I don't know, maybe this is iron and this is wood, right? So we've got two different things with different masses and all kinds of stuff. And essentially, what we want to do is do our I total. And we're going to just simply sum up the two things, right? We're going to go I equals 1 to 2 of the two different things, okay? And now all we have to do is figure out what those things are. So I of the rod, or the handle, is equal to 1/3, I said third and wrote half, mass of the handle times L squared. Okay, and we can put that a little W on mass of the wood handle. Okay, so we've got our 1/3 mass of the wood handle. Okay, fine. Now we can do our I mallet. And I don't want to call the whole thing's a mallet. Should we call it the head of the mallet? Okay. So we're going to do that. That's going to be just as before. It's an object that is going in a circle, and we don't really know what's holding it in place, right? We're just dealing with this object going around in a circle. So that means the mass of the head of the mallet times the length plus this little distance d to the center of mass. Okay, so it's the length of the wooden stick plus the little distance d to get to the center of mass from the axis. So this is distance to the center of mass from the axis. All right, so, oh, and we got to square it. Don't forget that. Now, we can then figure out our I total, and that's 1/3 mass of the wood times the length squared plus our mass of the hammerhead, the head of the hammer, times L plus D squared. And that ends up being our total moment of inertia for this hammer. You can try and do some things where you square and simplify and do all that stuff, but it's not going to look any prettier than this after all your algebra. So this is pretty much the way you might want to leave it if you're ever in this situation. Okay, so I want to end there, and I'm going to come back a little bit later, or maybe on this Thursday we'll talk about torque, and we'll start getting into other things, torques and all the other rotational stuff.